So in the beginning of this chapter, hypergeometric summation, we have a actual theorem. This is the statement of the theorem. So let pi be recurrence operator for f and k, and if Sn is equal to summation I from 1 to t ai pi, okay, and k minus I c, okay, does not depend on capital K small k, then Sn is a recurrence operator for the summation, okay, whenever k limit k from plus minus infinity cf is equal to 0, okay. So this is the statement. We have already give this statement, and using this statement we solve two actually example. We have discussed two example related with this proposition, okay. So now we need this proof of this proposition for our further discussion. So therefore I am going to discuss the proof of this proposition today, okay. So this is the statement. The PAB recurrence operator f and k, and Snn, this is our Snn. Snn is given in this way: I from 1 to t ai pi, okay. This is the statement actually. K minus I c, okay, does not depend on capital K small k. Then Snn is a recurrence operator for the sum Sn, small sn, okay. This is the f and k, summation f and k, whenever limit k tends to plus minus infinity c and k f and k equal to 0. So what does it imply actually? So you see this, what does it imply? So limit k tends to plus minus infinity f and k is equal to 0 means this f and k, this summation sign f and k contains a finite number of non-zero parts, okay, finite number of non-zero parts, and that is the sum extends over finite range, that is k from minus n to plus n. If this is happen, then we say that f and k becomes eventually 0, okay. F and k becomes eventually 0, that is you can write down f and k is equal to 0, something like that, and or when 0 as k tends to plus minus infinity, or this is another symbolic representation of this statement, okay. So here actually what does it imply in our discussion? So this is actually k from plus minus infinity c and k f and k equal to 0 means this actually this summation, okay, this summation contains a finite number of non-zero term, okay, finite number of non-zero term, this summations. This is the corresponding actually notation for our discussion. So it is given that Snn is this is the Snn, does not depend on small k or capital K small k, this is comma, okay, this is comma, so small k or capital K small k, okay. So now you consider z and k, this is equal to z and k, suppose this is this cf, okay, cf, something like that, z and k is equal to cf, cn comma k cf. So what is this Sn and f and k? What is this Sn and f and k? So just put the value of Sn, this is the value of Sn, f and k. Now we discuss one thing. This is the p1, these are actually recurrence operator, p1 p2, okay, these are recurrence operator, p1 p2 up to pt, these are recurrence operator, okay. So therefore you just consider this is a recurrence operator, therefore you observe that the multiplication of this recurrence operator, p is a recurrence operator, then so is every left multiplication, okay. So this is the observation we discussed. So you can see if p is a recurrence operator, then so is every left multiple ap, okay. We already established this result, and this idea can be implemented for a finite number of cases. So if p1 p2 are these are the recurrence operator, then so is every combination, that is a1 p1 up to ATPT. So therefore this is also a recurrence operator, this part is also a recurrence operator. So recurrence operator means recurrence operator of f means pi f equal to 0. So this is a recurrence operator of f means this of this equal to 0, okay, this of this equal to 0. So we have this part only, k minus I c f and k, k minus I c f, but cf is nothing but our g and k. So this is actually k is nothing but a shift operator. Okay, so one position will be shifted. So this is k of z and k means z and k plus 1, and I means the identity operator. So identity shift operator, this is z and k. So you can write down this expression. This can be written in this way. So therefore we have to show that s and n is a recurrence operator of small sn. Therefore Sn and small sn must be equal to 0. Our objective is to show that this part equal to 0. So what is Sn? This is our small sn. So since k is independent of this term, therefore you can take this term inside to the summation sign Sn f and k. But this is Sn and f and k is nothing but Sn and f and k is nothing but this. So this, by the given condition, it is already given that limit of cf, that is this part, limit of z, k tends to plus minus infinity equal to 0. So since this part equal to 0, it contains finite number of terms. So automatically, since 0 means this part is also equal to 0, because it is we have this statement. We have this statement, fn becomes eventually 0. F and k, if I am going to write down this expression, that f and k becomes eventually 0, that is this is actually equal to 0. Okay, so this is equal to 0 means this. So this is nothing but the definition of recurrence operator. So Snn is a recurrence operator for, so Snn is a recurrence operator for Sn. So hence the result. Okay, so I will upload the next discussion in the next video.